Introduction. Ravi, can you please open the window? Let some fresh air come into the room.
Sure, Father.
Father, when the sunlight comes from the window, why are the dust particles visible? Because air is a colloid, as it carries dust particles. These dust particles scatter the light. They have large size and are visible to naked eye. These particles seem to be floating zigzag in the air. This phenomenon is also known as Tyndall effect.
Okay, Father. I got the answer of my question. And I want to know more about this.
Son, to know more about this, you have to explore surface chemistry. Students, today we will study more about the surface chemistry. Objectives. At the end of this lesson, you will be able to define surface chemistry, understand mechanism of adsorption, classify adsorption, know about applications of adsorption, define and classify catalysis, analyze mechanism of enzyme catalysis, define and classify colloids, know the methods for preparation of colloids, explain properties of colloidal solution, define Tyndall effect and electrophoresis, define emulsions, know about applications of colloids. Definition. Surface chemistry is that branch of physical chemistry which deals with the study of the phenomena occurring at the interface, that is, the boundary separating two bulk phases. Solid-solid, solid-liquid interfaces are known. As gases are completely miscible, they do not form any interfaces. Interface is only a few molecules thick, but the area is dependent on the particle size of the bulk phases. Adsorption. The phenomenon of attracting and retaining the molecules of a substance on the surface, or a liquid or solid, leading to a higher concentration on the surface in comparison to the bulk, is called adsorption. For example, when oxygen gas is taken in a closed vessel containing powdered charcoal, then the pressure inside the enclosed vessel decreases. This is due to adsorption of the gas molecules on the surface of charcoal. The substance accumulating at the surface of the solid during adsorption is called adsorbate. The surface on which adsorption occurs is called adsorbent. Adsorption and absorption. The phenomenon in which a substance is uniformly distributed throughout the bulk is known as absorption. It is the penetration of the substance through the surface into the bulk of the solid. For example, when a sponge is dipped in a liquid, it absorbs some molecules of liquid. Let's make some important differences between adsorption and absorption. Adsorption involves unequal distribution of the molecular species in bulk and at the surface, whereas absorption involves uniform distribution of the molecular species throughout the bulk. Adsorption is rapid in the beginning and slows down near the equilibrium, whereas absorption occurs at a uniform rate. Adsorption is a surface phenomenon, whereas absorption occurs throughout the body of material. Sorption and desorption. Sorption. Sometimes the adsorbate dissolves into adsorbent. Initially, the adsorbate appears on the surface of adsorbent and later passes into the body of adsorbent. Thus, adsorption changes into absorption. Simultaneous occurrence of absorption and adsorption is called sorption. Desorption. The process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. Mechanism of adsorption. The amount of heat evolved when 1 mole of the adsorbate is adsorbed on adsorbent surface is called enthalpy of adsorption. Adsorption is always an exothermic process, and enthalpy change of adsorption is always negative. When adsorbate molecules are adsorbed on the surface of an adsorbent, their freedom of movement becomes restricted and hence entropy decreases. Adsorption is spontaneous. Therefore, at constant temperature and pressure, Gibbs free energy decreases. Delta G is equal to delta H minus T delta S. Types of adsorption. Depending upon the nature of forces existing between adsorbate molecules and adsorbent, the adsorption can be classified into 2 types: physical adsorption and chemical adsorption. Physical adsorption. If the forces of attraction existing between adsorbate and adsorbent are van der Waals forces, the adsorption is called physical adsorption. Since the forces existing between adsorbent and adsorbate are very weak, therefore, this type of adsorption can be easily reversed by heating or by decreasing the pressure. Chemical adsorption. If the forces of attraction existing between adsorbate particles and adsorbent are almost of the same strength as chemical bonds, the adsorption is called chemical adsorption. Since forces of attraction existing between adsorbent and adsorbate are very strong, therefore, this type of adsorption cannot be easily reversed. Comparison between physisorption and chemisorption. The important difference between physisorption and chemisorption are: low enthalpy of physisorption, usually of the order of -25 kJ per mole, whereas high enthalpy of chemisorption, usually of the order of -200 kJ per mole. In physisorption, forces of attraction are van der Waals forces, whereas in chemisorption, forces of attraction are chemical bond forces. Physisorption usually takes place at low temperature and decreases with increasing temperature, whereas chemisorption takes place at high temperature. Physisorption is reversible, whereas chemisorption is irreversible. Physisorption is related to the ease of liquefaction of the gas, whereas in chemisorption, the extent of adsorption is generally not related to liquefaction of the gas. Physisorption usually forms multimolecular layers on the adsorbent, whereas chemisorption usually forms monomolecular layers on the adsorbent. Physisorption does not require any activation energy, whereas chemisorption requires activation energy. Adsorption isotherm. The variation in the amount of gas adsorbed by the adsorbent with pressure at constant temperature can be expressed by a curve termed as adsorption isotherm. At low pressure, the graph is nearly straight and sloping. Hence, the extent of adsorption x upon m is directly proportional to the pressure of the gas. This can be expressed as x upon m is directly proportional to P raised to the power 1. At high pressure, saturation of the adsorbent surface occurs, and then amount of adsorption does not depend upon the pressure of the gas. This can be expressed as x upon m is directly proportional to P raised to the power 0. Freundlich isotherm. In the intermediate range of pressure, x upon m will depend upon P raised to the powers between unity and 0. This can be expressed as x upon m is directly proportional to P raised to the power 1 to 0, or x upon m is directly proportional to P raised to the power 1 upon n, where value of n is greater than 1, or it can be written as x upon m is equal to k multiplied by P raised to the power 1 upon n. K and n are constant, whose value depends upon the nature of gas and the adsorbent solid at a particular temperature. Taking logarithm on both sides, we get log x upon m is equal to log k plus 1 upon n log p. The graph between log x upon m and log p is a straight line. The slope of the line is equal to 1 upon n, and the intercept on log x upon m axis will correspond to log k. Applications of adsorption. Gas masks. These contain activated charcoal or a mixture of adsorbents and are used for breathing in an atmosphere containing poisonous gases. Removing of coloring matter. Animal charcoal removes colors of solutions as coloring impurities are preferentially adsorbed on charcoal. For example, bone charcoal is used as decolorizer in sugar industry. Controlling humidity. Silica and alumina gels are used as adsorbent for removing moisture and controlling humidity. Adsorption indicators. Dyes like eosin and fluorescein are used as indicator in titrating bromide solution with AgNO3, precipitate of silver halide, as the property of adsorbing these dyes and thereby producing characteristic deep colors at the end point in the titration. In curing of diseases. A number of drugs kill the germs by getting adsorbed on them. Removal of hardness of water. Ion exchange resins are used for removal of hardness of water. Some other applications of adsorption. Heterogeneous catalysis. There are many gaseous reactions of industrial importance involving solid catalyst. Adsorption of reactants on solid surfaces increases rate of reaction. For example, manufacture of ammonia, sulfuric acid, and hydrogenation of oils. Chromatographic separation. Components of mixtures, especially of organic compounds, can be separated and identified by chromatographic analysis, which is based upon adsorption phenomenon. For example, thin layer chromatography, paper chromatography, and gas-liquid chromatography. Froth flotation method. Pulverized ore is suspended in water containing some pine oil and a frothing agent. When air is blown into it, the ore particles are adsorbed on the air-oil interface and come to the surface in the form of froth. For example, sulfide ores are concentrated by this method. Separation of inert gases. Due to difference in the degree of adsorption of gases by charcoal at different temperatures, a mixture of inert gases can be separated by adsorption on coconut charcoal. Catalysis. A catalyst is a substance which influences the speed of a chemical reaction without itself undergoing any chemical change at the end of the reaction. This phenomenon is known as catalysis. For example, when potassium chlorate is heated in the temperature range of 653 to 873 Kelvin, it slowly decomposes to give dioxygen. But if a little manganese dioxide is added, the decomposition takes place in the temperature range of 473 to 633 Kelvin and dioxygen is released at a much faster rate. A catalyst may increase or decrease the rate of a reaction. A catalyst which increases the rate of reaction is called a positive catalyst. For example, decomposition of KClO3 in presence of MnO2. A catalyst which decreases the rate of reaction is called a negative catalyst. For example, tetraethyl lead is added to petrol to prevent knocking of the engine. Types of catalysis. The catalysis reactions are of two types: homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis. When the reactants and the catalyst are in the same phase, it is called homogeneous catalysis. For example, oxidation of sulfur dioxide into sulfur trioxide in presence of nitric oxide in the lead chamber process for the manufacture of sulfuric acid. Reactants, sulfur dioxide and oxygen, and the catalyst, nitrous oxide, are all in the same gaseous phase. Heterogeneous catalysis. When the reactants and the catalyst are in the different phase, it is called heterogeneous catalysis. For example, manufacture of methanol from carbon monoxide and hydrogen using ZNO plus Cr2O3 as catalyst. Reactants are in gaseous phase and catalyst is in solid phase. Adsorption theory of heterogeneous catalysis. In heterogeneous catalysis, the catalytic activity is localized on the surface of the solid catalyst. Heterogeneous catalysis occurs through the following steps: diffusion of reactants to the surface of the catalyst, adsorption of reactants on the surface of the solid catalyst. The adsorbed reactant molecules undergo a chemical reaction to form an intermediate called activated complex. The activated complex then breaks to form the products. The products then dissociate from the catalyst surface, known as desorption. Diffusion of product molecules away from catalyst surface. Nature of solid catalyst. Metals, alloys of metals, metal oxides, metal sulfides, or mixture of these are generally used as solid catalyst. The two important aspects of solid catalysts are activity. The ability of a catalyst to accelerate the rate of a chemical reaction is called activity. These catalysts accelerate the rate of reactions to a very large extent, and in some cases, the rate of reaction becomes 10 raised to the power 10 times faster in the presence of a catalyst. For example, a mixture of pure H2 and O2 does not react, but in presence of catalyst platinum, they combine to form water and the reaction takes place with explosive violence. Selectivity. It is the ability of a catalyst to direct a reaction to yield a particular product. For example, carbon monoxide and hydrogen react to give different products in presence of different catalysts. Shape selective catalysis by zeolites. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecules is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb-like structures. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atoms. The reactions taking place in zeolites depend upon the size and shape of reactant and product molecules as well as upon the pores and cavities of the zeolites. Zeolites are used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization, enzyme catalysis. Enzymes are complex nitrogenous organic compounds which are produced in living cells of plants and animals. They are also known as biochemical catalysts because of their importance in biochemical processes. Almost all enzymes are complex protein molecules with high molecular mass. Enzymes are produced by living cells. A typical cell, on an average, contains about 3,000 different kinds of enzymes. each enzyme catalyzing a particular reaction. For example, conversion of milk into curd by lactobacilli enzyme present in curd. Characteristics of enzyme catalysis. Enzymes form a colloidal solution in water, and hence they are very active catalysts. Like inorganic catalysts, they cannot disturb the final state of equilibrium of a reversible reaction. They are highly specific in nature. One catalyst cannot catalyze more than one reaction. They are highly specific to temperature. The optimum temperature of their activity is 35 degrees Celsius to 40 degrees Celsius. They are deactivated at 70 degrees Celsius. A small quantity of enzyme catalyst is sufficient for a large change. They are destroyed by ultraviolet rays. Their efficiency is decreased in presence of electrolytes. Assessment. Before proceeding further, let us know how much you have learnt. Drag and drop the correct option. Mechanism of enzyme catalysis. The enzymes are highly specific in their action. The specificity of an enzyme is due to presence of some specific sites called active sites. These active sites are associated with the presence of some functional groups which undergo some weak interactions with the substrate molecule. The shape of active site on a given enzyme is such that only a specific substrate can bind with it. This specific binding of the active site with the substrate results in the formation of enzyme-substrate complex. In this complex, the substrate molecules are held in appropriate steric orientation to facilitate the reaction. After achieving proper orientation, substrate molecules react to form the products. As product molecules do not have affinity for the enzyme surface, they immediately leave the surface so that fresh substrate molecules bind with the active site. Colloids. A colloid is a heterogeneous system in which one substance is dispersed as very fine particle having diameters in the range of 1 to 100 nanometer in a continuous medium of another substance. For example, milk, shaving lather, jelly, and paint. A colloidal solution is heterogeneous in nature and always consists of at least two phases, the disperse phase and the dispersion medium. Disperse phase. It is the component present in small proportion and consists of particles of colloidal dimensions. Dispersion medium. The medium in which colloidal particles are dispersed is called dispersion medium. Classification based on physical state of colloids. Dispersed phase and dispersion medium can be solid, liquid, or gas. Therefore, 8 types of colloidal system are possible depending upon the physical state of the dispersed phase and the dispersion medium. Rock salt is an example of solid sol. Paint is an example of sol. Smoke is an example of aerosol. Cheese is an example of gels. Milk is an example of emulsion. Fog is an example of liquid aerosol. Rubber is an example of solid foam. Soap lather is an example of foam. Classification based on nature of interaction in colloids. On the basis of nature of interaction between dispersed phase and the dispersion medium, colloids are divided into two categories. Lyophilic colloids. Particles of dispersed phase have great affinity for the dispersion medium. They are self-stabilized because of strong attractive forces operating between the suspended particles and the dispersion medium. They are reversible in nature. They are also known as intrinsic colloids. For example, gums, starch, gelatin, and albumin. Lyophobic colloids. Particles of dispersed phase have no affinity for dispersion medium. Rather, they hate dispersion medium. They are not easily prepared and need stabilizing agents for their preservation. They are irreversible. They are also called extrinsic colloids. For example, salts of gold, silver, and ferric hydroxide. Classification based on type of particles of dispersed phase. On the basis of nature of the particles of dispersed phase, colloids are divided into three categories. Multimolecular colloids. In this type of colloids, colloidal particles are aggregates of atoms or small molecules with molecular size less than 1 nanometer. These molecules in the aggregate are held by van der Waals forces. For example, a gold salt consists of particles of various sizes, which are clusters of several gold atoms. Macromolecular colloids. In this type of colloids, colloidal particles are themselves large molecules having colloidal dimensions. They have very high molecular masses, varying from thousands to millions. For example, proteins, cellulose, nylon, and plastic. Associated colloids. This type of colloids behave as normal, strong electrolytes at low concentration, but at higher concentration, they behave as colloidal solutions due to the formation of aggregated particles known as micelles. For example, soaps and detergents. Mechanism of micelle formation. The formation of micelles takes place only above a particular concentration, called critical micelle concentration, and above a particular temperature called Kraft temperature. Micelles are formed by surfactant molecules. These molecules have lyophilic as well as lyophobic ends. For example, sodium stearate. When soap solution is dilute and the concentration is below its Cmse, sodium stearate behaves as a normal strong electrolyte. When the concentration exceeds Cmse, the non-polar tails of the anion clump into the center of a ball-like structure called a micelle, because these are hydrophobic. The polar head of the molecule presents itself for interaction with the water molecules on the outside of the micelle. This type of micelle is known as normal phase micelle. Inverse micelles have the head group at the center with the tails extending out. These are formed in non-polar media. Preparation of colloids by chemical methods. Colloidal solutions can be prepared by chemical reactions involving double decomposition, oxidation, reduction, and hydrolysis. Double decomposition. A colloidal sol of arsenious sulfide is obtained by passing hydrogen sulfide into a solution of arsenious oxide in distilled water. Oxidation. A colloidal solution of sulfur can be obtained by passing hydrogen sulfide into a solution of sulfur dioxide in water or through a solution of an oxidizing agent. Reduction. A colloidal solution of a metal can be prepared by reducing its salt solution with a suitable reducing agent. Hydrolysis. This method is used to prepare hydroxides and oxides of weakly electropositive metals. A red sol of ferric hydroxide is obtained by the hydrolysis of ferric chloride with boiling water. Preparation of colloids by electrical disintegration. This process is also known as Bredig's arc method. It involves dispersion as well as condensation. Colloidal solutions of metals can be prepared by this method. In this method, electric arc is struck between electrodes of the metal immersed in the dispersion medium. The intense heat produced vaporizes some of the metal, which then condenses to form particles of colloidal size. Preparation of colloids by peptization. Peptization is the process of converting a precipitate into colloidal form by shaking it with dispersion medium in the presence of small amount of electrolyte. The electrolyte used for this purpose is called peptizing agent. During peptization, the precipitate adsorbs one of the ions of the electrolyte on its surface. The adsorbed ion is generally common with those of the precipitate. This causes the development of positive or negative charge on precipitates, which ultimately break up into smaller particles having the dimensions of colloids. Purification of colloidal solutions. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. The purification of colloidal solution can be done by following methods. Dialysis. It is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. The apparatus used for this purpose is called dialyzer. Electrodialysis. The process of dialysis is quite slow. It can be made faster by applying an electric field if the dissolved substance in the impure colloidal solution is only an electrolyte. Then the process is known as electrodialysis. Ultrafiltration. In this method, colloidal solutions are purified by carrying out filtration through special type of graded filters called ultrafilters. These filter papers allow the electrolytes to pass through them but do not allow colloidal particles. Properties of colloidal solutions. Colligative properties. Due to high average molecular masses of colloidal particles, they give very low mole fractions in colloidal solutions. Hence, they possess very low values of colligative properties. Filtrability. The size of the colloidal particles is less than the pores of the filter paper, and therefore, they easily pass through a filter paper. They cannot pass through the UF membrane. Tyndall effect. When a strong beam of light is passed through a true solution, it cannot be seen unless the eye is placed in the path. However, when the same beam of light is passed through a sol, the path of light becomes visible with a bluish light. This phenomenon is called Tyndall effect. This phenomenon is due to scattering of light from the surface of colloidal particles. Colloidal particles are too small to be seen with naked eye. They scatter light and become visible as bright spots or disks of light against a black background when viewed through an ultramicroscope. Brownian movement. When colloidal salts were observed under a microscope, scattered light was seen moving in a zigzag motion. As the light is scattered by colloidal particles, these particles execute ceaseless, erratic random motion called Brownian movement. It is due to the bombardment of colloidal particles by the molecules of the dispersion medium. Due to Brownian movement, the colloidal particles do not settle down under the force of gravity, and therefore, it is an important factor for the stability of the sol. Electrophoresis. The particles of the colloidal solution are electrically charged. The existence of the electric charge is shown by the phenomenon of electrophoresis. It involves the movement of colloidal particles either towards the cathode or anode under the influence of electrical field. The colloidal solution is placed in a U-tube fitted with platinum electrodes. On passing an electric current, the charged colloidal particles move towards the oppositely charged electrode. Coagulation of colloidal solution. The precipitation of a colloid through induced aggregation by the addition of some suitable electrolyte is called coagulation. The coagulation of a colloidal solution by an electrolyte does not take place until the added electrolyte has certain minimum concentration in the solution. The minimum concentration of the electrolyte in millimoles that must be added to 1 liter of the sol so as to bring about complete coagulation is called the coagulation value of the electrolyte for the sol. Different electrolytes have different coagulation values. Smaller the coagulation value of the electrolyte, larger is its coagulating power. Emulsions. An emulsion is a colloidal dispersion in which both dispersed phase and the dispersion medium are liquid. In an emulsion, fine droplets of one liquid are dispersed in a continuous medium of another liquid. Emulsions are of two types: oil in water and water in oil. Oil in water. In these emulsions, some droplets of oil are dispersed in water. For example, milk is oil in water type of emulsion, in which liquid fat is the dispersed phase and water is the dispersion medium. Water in oil. In these emulsions, water is the dispersed phase and oil is the dispersion medium. Stiff greases are emulsions of water in oil type, in which water is dispersed in lubricating oil. Colloids around us. Colloids play very significant role in nature and our daily lives. Some important examples are as follows. Blue color of the sky. It is due to scattering of light by colloidally dispersed dust particles in air that sky looks blue. Fog and mist. They are colloidal systems. When large mass of air containing dust particles cools below its dew point, the moisture present in the air condenses on the dust particles, forming fine droplets. Food items. Most of the food items are colloidal in nature. Blood. It is a colloidal solution of an albuminoid substance. Soils. Fertile soils are colloidal system, and on account of their colloidal nature, soils adsorb moisture and nourishing materials for plants. Paints. All paints are colloidal dispersions of solid pigments in a liquid medium. Medicines. Many medicines are colloidal in nature. The medicines in colloidal form are easily adsorbed by body tissues and are more effective. Digestion of fats. The digestion of fats is aided by emulsification. Applications of colloids. Due to the presence of electrical charge on colloidal particles, they are good conductors. Some important applications of colloids are rubber plating. The negatively charged rubber particles from the rubber sole are deposited on wares and handles of different tools by electroplating. Sewage disposal. Sewage water contains particles of dirt, rubbish, etc., which are of colloidal size, carry charge, and therefore do not settle down easily. These particles can be removed by electrophoresis. Cottrell smoke precipitator. Smoke is made free of colloidal particles by passing it through Cottrell precipitator installed in the chimney of an industrial plant. Formation of delta. When river water comes in contact with seawater, coagulation of colloidal particles occurs. These coagulated clay particles settle down at the point of contact and gradually river bed starts rising. Artificial rain. It is caused by spraying oppositely charged colloidal dust or sand particles over the clouds. The colloidal water particles of the clouds get neutralized and coagulate to bigger water drops which cause artificial rain. Purification of water. The colloidal particles present in water can be precipitated by addition of small amount of alum. The Al+3 ions furnished by alum help in coagulation of impurities which are present in the colloidal form. Assessment. Before proceeding further, let us know how much you have learnt. Drag and drop the correct option. Did you know? Bone black and charcoal are used in industry to remove colors from solutions since they adsorb many coloring materials. Sometimes, the smoke emitted by motorcycles seems to be blue in color, is an example of Tyndall effect. The enzyme tylenine, found in human saliva, accelerates the reaction so that starches can be digested. The clotting of blood is an example of coagulation. Summary. Let us summarize what we have learnt. Surface chemistry is that branch of physical chemistry which deals with the study of the phenomena occurring at the interface. The phenomenon of attracting and retaining the molecules of a substance on the surface, leading to a higher concentration on the surface in comparison to the bulk, is called adsorption. A catalyst is a substance which influences the speed of a chemical reaction without itself undergoing any chemical change at the end of the reaction. The enzymes are highly specific in their action. The specificity of an enzyme is due to presence of some specific sites called active sites. A colloid is a heterogeneous system in which one substance is dispersed as very fine particles in a continuous medium of another substance. Peptidization is the process of converting a precipitate into colloidal form by shaking it with dispersion medium in the presence of small amount of electrolyte. The precipitation of a colloid through induced aggregation by the addition of some suitable electrolyte is called coagulation. An emulsion is a colloidal dispersion in which both dispersed phase and the dispersion medium are liquid.